Unfortunately, we have been interrupted by factors beyond our ability to control. So how much more we learn before the end of the term is going to depend on how much time we have left. I'm interested in two main topics. The first one of it will be covered largely today and next lecture. And then the last one, and that one is the gradient divergence of curl, integral theorems of calculus. So we will look at those ones. Then the last thing that I want to cover, if time permits us, is the transport theorem due to Reynolds and Leibniz. I wish we can cover that too. But if we cannot, we leave it. But that is, last lecture was done on the 14th of February, on Valentine's Day. That lecture was before the strike, but few people attended. My temptation in today's lecture is to go over that, but I will not yield to that temptation. I'm not going to go over that lecture because I listened to the lecture myself yesterday again, and my opinion is that I can't do better than that. So if you miss that lecture, it is your deep business to go and take the tape and listen to it, look at the slides. And if you have questions, post the questions as much as we can. We'll try to answer your question, but I'm not going to go over them because I went over it once, I recorded it, I sent you the slides, and I taught it. So that is good enough. If there are any difficulties about that, I will be glad to learn about it as if there's anything I can still do to help you. Today, we are looking at integral calculus of fields. We have been looking at differential calculus. We have been looking at what a derivative is. We started from secondary school when we were introduced to the idea of derivative as the limit of a quotient. And what is up is a scalar, what is down is a scalar. The function we are talking about is a uniaxial function of a single scalar variable. Of course, at this point in your lives, you know that we can have function of multiple variables. But more importantly, is when the function of multiple variables is actually the function of three variables, which are the coordinate locations in the Euclidean point space. That is the most important problem to the engineer, not just arbitrarily choosing three variables. When the variable is the Euclidean space, the space where we all live and do our work, when those are the variables involved, then we are looking at fields. We call those ones fields. I will give you a more formal definition of fields shortly, but that is what is really of great importance to us. Sometimes we also want to add another variable, time, to it. When you look at that, you are solving the same problem of a multivariable calculus problem, but you are doing it in a particular form that allows you to use vector theory. And that actually makes a lot of things easy, and that is the way to go. And most of the results of multivariate calculus will come out anyway. So there's scarcely any result in multivariate calculus that you will also not come to see as a result of working in this way. So it's a win-win situation in all ways. Some people have been asking me, what are recommended textbooks? The books that I use, I've read them over and over and over. I've abstracted what I consider to be important things there. It is not likely that we will make a lot more progress going directly to many of those books, but it is possible that there is something that I really explain well enough that the way I explain it does not suit your fancy, and somebody else explaining it will be better for you. Therefore, I have listed 4 books. There are many other books. You can take any book. Advanced Calculus, especially for engineers, is a very well-researched subject. There are so many books out there. But the ones I am giving you are the ones that I actually used. The first one that I will recommend is the book I have written myself. That is Continuum Mechanics for Modeling, Simulation, and Design. And that book starts with advanced calculus issues, tensor and advanced calculus. And what we are doing there is to cover the weaknesses that we think students have. And it is those weaknesses that this course is supposed to bridge. So there is a commonality of purpose there. Another good reason to look at that book is that that book shows you where this calculus is going. Sometimes engineers just learn math and they do not even know why they are learning math. When you read math from the point of view of continuum mechanics for modeling, simulation, and design, you can see where the math is going. And that is an advantage for you, so that you are not just chasing math anyhow. You are not a mathematician. Well, to be an engineer, you will be a mathematician to some extent, but you are not just looking at math for its own sake. You are looking at math for a specific purpose, to be able to solve engineering problems which will require modeling, simulation, and design into this world. Then the second book is Mathematics of Physics and Modern Engineering. That book is a bit dated now. That's the book I used myself as an undergraduate, but it is a classic. It's a very, very good book. I still keep my own copy, even though I was in your level several years back, but I still have my own copy. The book is good, but the book will not reach the level we are reaching, because when that book was written, like 50, 60 years ago, when the book was written, there was no Android, there was no symbolic algebra, there was no Python. So we are bringing modern things that the authors of these books did not envisage into this course. So when you take a book, most calculus books are written long ago, and even the ones that are written these days do not really seem to improve. So in this course, you would have noticed that we are using all sorts of other skills apart from just mathematics to bear on the work we are doing. We do graphics, we do symbolics, we use computers to calculate things, and so many things. But that book is good. Another book that I use myself, that I have read a lot of, is Advanced Calculus by Spherical. It's a short outline series. I'm sure you should have been familiar with that by now. That is another old book, which has been in existence since I myself was an undergraduate. Then the last book recommended is The Mathematical Guidebook for Symbolics by Michael Trott Springer. If you can lay your hand on that book, it's a fantastic manual that will take you beyond even what we are doing in Mathematica, that can really make you an expert in using Mathematica as an engineer. So I will introduce other materials later on, but this is to satisfy the people that are bugging me, give us book, give us book. I hope these 4 books will take you off my back for a while, and I can have some peace. The next thing is that when I was looking at the homework assignments, one thing I realized is that when I was looking at the last lecture notes, I hinted that you should do something on this page. There's a page of it that is like this, when I dealt with the spherical octant. After working with the spherical octant and look at the surface here and perform some integrations on it, I said, okay, if you look at an orange, you can cut an orange into 2. You can slice this again into another 2, or vertically, 2 vertical slices. Then you can cut it horizontally. So that means you have 8 pieces. You can count counterclockwise. The first 4, you can take 1 and go counterclockwise and count for 1, 2, 3, 4. And then you can come down again and count counterclockwise 1, 2, 3, 4. So there are 8 octants. As a practice, I want you to try to find the domains of those 8 octants in any coordinate system you are using, whether it is Cartesian coordinates or spherical coordinates or cylindrical coordinates. Try and see and perform the same integral. For instance, if I tell you to find the volume of the first octant and you find the volume of the first octant, you should get the same result by changing the domain to coincide with the second octant, for instance. If you can do that, you are beginning to understand the fundamental issue that matters when you are doing multiple variables, because it is the specification of the domain that is the issue. What I am going to do after today's lecture is that I'm going to add 20 questions, around 20 to 40 questions around the specification of the domain of the octant and some simple figures that you have come across. 40 questions, and all those questions will be asking is that it will give you a definition of an octant and tell you to find the surface that are bounding it. And it will give you in a quiz form, and then you will choose. So if you do this homework, you will know how to get through that kind of thing. So, but I asked you to do it last February, And I said I present to you first the mathematical code. This is the mathematical code, for instance, that generated this first octant. You can just change some few parameters and generate the second octant, generate the third octant, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth, and the eighth. There are 8 of them. And I want you to submit that as a homework assignment. So that's homework, and that is due next Monday. So submit that as homework assignment to your class reps, who will bring it to Mr. Yuade, so that it will be passed on to me. Because I find that many times people don't seem to take these things seriously, and that could affect you in the exam. So what I'm going to be adding 20 to 40 questions around that. So I just want you to be warned so that you will be able to answer those questions when you see them. Now, in order to go to today's class, I just want to remind you that last lecture, we said we were going on an integral journey. Our integral journey begins with the ordinary integral, which you started in your secondary school, you did in your 100 level, and perhaps some of it in your 200 level. And the domain is a subset of x-axis, and the function is a function of a scalar quantity. That is your first notion of integrals when you are introduced to integral as the limit of sums. It's usually areas under a particular curve. But I have tried to emphasize the fact that integral, the idea of integral goes far beyond the area under a curve. It is much more fundamental to see it as the limit of a sum, as your domain becomes, your domain of subdivision becomes as small as possible. From there, the next bus stop was the area integral, where your domain is the subset of the XY plane or another coordinate plane, a single plane. And that introduces you to double integrals. The next thing was a volume integral, when your domain was a subset of the 3-dimensional Euclidean point space, which introduced us to triple integrals. There we could use Cartesian coordinates, we could use spherical polar coordinates or cylindrical polar coordinates, or any other coordinate system that may suit our fancy. From that point on, we moved to line integral. Before I move further, please note that I expect you to use the chat room a lot. As I'm moving on, I will be visiting the chat room once in a while. If I see a question that does not take me too far away from the class, I might answer it here. Or I take a look at all the chats after the lecture. And if there is anything that is important enough that is recurring in the chats that's not answered, it is likely that I either bring it up in my next lecture, or I might actually add that idea into some lecture down the road, or meet you one way or the other. So if you also can identify yourself, it make it easy, but it's not really absolutely necessary. Just know that I use the chat, and the administrator of this site is going to record all the chats, and I'm going to use them. Even in that chat, as long as you are sensible enough and you are not going beyond your bounds, you are free to make suggestions and say things that could be of benefit to yourself and to other people in the class. So please use the chat room. I will visit it once in a while, and I will surely look at it during the break time when I'm a little bit freer. The next thing we looked at was the line integral. And the line integral is quite interesting because we are integrating along a particular curve in the 3-dimensional Euclidean point space. Contrary to the approach in textbooks generally, where they will first of all take the line integral on a plane and then generalize to the 3 dimensions. We go the opposite. We look at the most general form of line integral and then we specialize it to a plane. I think you might find that to be much more natural because line integrals occur, a curve can occur anywhere in the 3 dimensions. It doesn't have to be constrained to a plane. Then, just before by the time the strike was on, where we were to go to was surface integral. 3-dimensional Euclidean space is the domain, and then the surface integral is a more complicated form of a line integral, and it requires a lot more effort to understand than line integrals, but it's important. And when you have looked at all those, then we can go to integral theorems. Today's class we are going to try and take both the surface integral and integral theorems at the same time. And I think one of them, they help each other. And we will not finish I have 55 or 56 slides, so we can't finish those slides today. So again, avail yourself of opportunity to ask me questions. And if you have questions, I might take a look at those questions when I have the opportunity to do so. So let me just see. I'm saying some, you started from the beginning of the session or continuation. Somebody doesn't understand the idea. Okay, good. I am not starting, I'm starting at the end of the last lecture. So if you didn't attend that lecture, it is your business to go and take the video and watch it. It's not mine. I've done my own duty at the end of it. So the question is, are you starting from the beginning of the session or continuation? I don't understand this question though. Somebody doesn't understand the assignment. Okay. The assignment, let me go back to the assignment again, the assignment that I have in mind. The assignment is that if you look at this code here, if you look at the mathematical code on the second slide, the mathematical code on the second slide creates a domain for the first octant in a sphere. I want you to plot the second octant of that same sphere this way. Plot the third octant, plot the fourth octant, the fifth octant, the sixth octant, the seventh octant, and the eighth octant to demonstrate that you know how to specify the surfaces that bound those octants. I've showed you with the code how to do it for the first octant. It is just now for you to go and look at how you can do it for the other octants. And that is the assignment. And you are supposed to write the mathematical code, get the results, and print them out and submit to your class rep. I hope that is clear. Let me just see whether that is clear to everybody now. Can you see it again? That is it. You are looking at it now. How do we submit? Submit to your, no, you submit hard copy. And I will ask for soft copy if I need to. I think basically, sorry, submit both soft and hard copies. I want to see both. Submit to your class rep. So I think I've answered that. So we can move on now. So I've looked at the integral journey, and you can see that today's class, we will look at surface integral and the integral theorems of Stokes, Gauss, and Gray. Now, I want you to know the approach we shall use. The approach we shall use here is to know that where we are going is the problem formulation in real engineering problems, which essentially result in differential equations. That is what an engineering student does for 5 years in the university. You are looking at scenarios and turning them to differential equations that can be solved. That is what you are doing in all the courses that mechanics of anything, whether mechanics of solids, mechanics of structures, mechanics of fluids, mechanics of heat, thermodynamics, mechanics of dynamics of rigid bodies, of structures, of buckling, everything. That's what you are doing in most of those courses. Now, many times you are told to find closed form solutions. You are told to solve the differential equations, and you are given simple boundary conditions. Those are just for historical purposes and for the classroom. When you go out there in engineering, the problems that you have cannot be solved that simply. So that's why you need computers, you need finite element analysis, which are numerical solutions. When you do numerical solutions, all the things you are cramming in the university or in your secondary school will not matter. You are always going to be referring to the fundamental definitions. You are going to be referring to the fundamental definitions. So a person who makes a first class by remembering all the ways that the closed form solutions work will likely fail as an engineer in practice, because that's not what matters. If you are trusting that too much, you will fail, because what matters is going back to the fundamentals and using numerical methods to solve the problem. So don't get too flattered because you are getting great grades by cramming and remembering how, for instance, you want to differentiate something, you already know the differential results, and then you cram it and you give it back to the teacher. Most of the time, when those things occur, the boundary conditions are usually so complex that you cannot solve them the way you solve them in class. So sometimes some of these problems can take weeks, months, years to come up with solutions because the solutions are complex. And usually that problem is coming from the boundary conditions. Consequently, our emphasis will not be to be expecting you to remember how to solve and remembering those things. But instead, I will emphasize the fundamental definitions. I will avoid proofs most of the time. Instead, I'm going to emphasize computational skills. If you understand what we are talking about, you know how it is defined, you know how to use it, and you have the computational skills to be able to get results from it using mathematical or some other numerical process. Those are the things that I am emphasizing. I'm not even emphasizing proofs. The only benefit as far as I'm concerned of proofs is for you to remember. If you can remember in some other way, good. I will give you proofs when necessary. I will give you some proofs, but that is not, just note that proofs are not my emphasis. My emphasis are on the fundamental definitions and computational skills that follow an understanding of what the fundamental definitions are, because those are the things that matter in real engineering practice. We will give proofs, and it will be good if you can follow the proofs because it will make you able to remember the fundamental definitions better. But apart from that, the proofs really affect you too much more than that. So let us then go back again to reiterating some of the things that we have learned before. What is a field? What is a field? You look at the Euclidean point space in concrete terms. We are showing you now the Euclidean point space in concrete terms. For instance, in the first picture here, you can see the south and north poles of a magnet. And if you have done this experiment before, that is an experiment so easy to do. Just get some iron filings and some other things, and you'll be able to see the lines of force. Most people do this thing in secondary school. Most people do these things in secondary school, and most schools are able to afford this. Even if your school can't afford it, you can get iron filings from any machine shop and put it on a sheet of paper with a magnet that you can buy, spread it on. You will see the iron filings will arrange themselves, and it will show you the lines of force. That shows that at any point in this plane, any point, any XY coordinate, there is a particular force that has magnitude as well as direction. For instance, where it is pointing to, when you are near the South Pole, it's pointing into the South Pole. When you are near the North Pole, it's pointing out of the North Pole. When you are in the middle, it's pointing horizontally, pointing from north to south, horizontally in parallels to them. This is an example of a Euclidean point space. And it's also an example of the field, because the field is the Euclidean point space in which at every point a particular vector or scalar or tensor is defined. Here it is the lines of force that are defined at every point. So this is a concrete example of a field. That is called a magnetic field. Now, those of you who watch television a lot, you would have had all the weather reporters telling you about areas of low pressure, high pressure, with a map of your country or any area, and then they will tell you there is low pressure here, there is high pressure here. In the place of low pressure, maybe rain will fall. Now, that at every point there is a particular value for pressure. That again is a Euclidean point space. And it's also a field because pressure is defined from point to point, having different magnitudes, having different values as we go from point to point. Then another one is the electric force field, which you can find along any cable that is carrying a current. You can see these fields are like this. If the current is coming out or going in, the direction of the fields will be the direction of the force, of the value of the force, of the electric force in any area is also shown. Another one is this interesting one, which is a velocity field in a fluid that is disturbed. So the arrows there are showing both the magnitudes and direction of the velocities as the motion is generated there. So this is another example of a concrete Euclidean point space, which is also a field. It is a field in this case because a velocity, take any point, a velocity vector is defined, it has magnitude and it has direction. So because of that, this is a Euclidean point space and it's also a field. So we are looking at fields here now in concrete terms. This is another example. This example was coming from a problem I did with some of the students who are taking design course, maybe postgraduate students, and they were looking at the temperature distribution on a disc brake. The disc brake is circular, but we have cut it into 4 quadrants. We have cut it into 4 quadrants since the conditions in each quadrant is the same. Instead of solving it for the whole circle, we can solve everything for a single quadrant and know that the result applies to the remaining 2 quadrants symmetrically. So you might be interested in the temperature field. You might be interested where the temperature field is a situation where at every point a temperature value is given as we move from point to point. That is the temperature field. A stress field is a tensor value of stress is available from point to point. For instance, you can see that even though in this place, the temperature at the point where you add the bolts is very, or this where you have these openings is very low, but the stresses are very high there. So you can see that the fact that you have low temperatures, which is shown in blue, doesn't mean that the stresses will be different. So the temperature field is completely different from the stress field, even though the causing, what is causing them is the same. What is causing the problem is the same. So, and then I've forgotten what this one is. No, let me just go back. This is another field. I'm not saying it. Let me just see whether I can move this. Yes, this is the displacement field here. This is the displacement field, and the displacement field, the factor of safety field. So you can have, whenever one particular quantity is defined at every point in a Euclidean point space, what you have is a field. What we are interested in is how do we apply calculus to fields? Because until you begin to apply calculus to fields, you are still warming up, you are joking. The engineering is the application of calculus to fields. You are looking for something. You are either looking for displacement, you want to know where this brake will break, where it will crack, or where there will be a problem. Those are the kinds of things that are of interest to the engineer. Where the displacements are very high, or where the temperature is too high, so that you can cool it down, and you can change the parameters to reduce the temperature distribution, to reduce the temperature gradient. Those are the kinds of things that are of importance. That is why our interest is application of calculus to fields. So you need to understand what a field is. A field is any Euclidean point space where a scalar like pressure or temperature, a vector like velocity or force or acceleration, or a tensor like, a vector like displacement or velocity or force, a tensor like strain or stress or velocity gradient, because velocity gradient is a tensor. Temperature is a vector, but temperature gradient is a vector. So you need to see how we move from, when you are taking the gradient of anything, you raise the order of magnitude by 1. So if you have a scalar and you take its gradient, you are going to get a vector. If you have a vector, you take its gradient, you are going to get a tensor. If you have a tensor, you take its gradient, you are going to get a third order tensor. You take a third order tensor, you take its gradient, you are going to, everything gets promoted by 1 when you take their gradient. So those are the kinds of things, but we are looking at how do you apply calculus to fields. In order to apply calculus to fields, you have to first of all understand the differential calculus of fields. That is something that includes directional derivative and gradient. We have spent some effort on that already. Then now we are looking at the integral calculus of fields. Then we are going to look at the integral theorems of Stokes, integral theorem of Gauss, and integral theorem of Green. Actually, you will find later that there are only two, that there are really only two integral theorems. That's of Stokes and Gauss. The Green's theorem will be a special case of Stokes' theorem, as you will find out later on in this course, or in this lecture, or subsequently. Let me just check the chart again to see whether the real difference between a vector and a tensor. Okay, you will know. Mr. What is his name now? Sam to everyone, Mr. Sam. Don't worry, you will know. If you don't know, who know no good.